Welcome back to the Deep Dive. Today we're wrapping up our series on the fundamentals of chemistry with a really fascinating topic.
We are indeed.
We're actually going inside the atomic nucleus, looking at reactions that are just worlds apart from the usual chemical ones we talk about.
That's right, it's nuclear chemistry.
So get ready, because this is where things get really interesting. Elements themselves can change identity.
And our mission today really is to unpack what makes these nuclear reactions tick. How are they different? How do we write them down using those specific symbols for isotopes?
Right, the balancing act.
Exactly. How do
Yeah.
we balance them? And then what are the implications, which are huge, by the way? Think stars, think elements being born, but also things like nuclear power and even medicine.
Yeah, it's everywhere when you start looking.
Yeah,
Our main source for this is a great chapter covering nuclear chemistry. It really lays it all out.
it does.
And here's where it grabs you, I think.
Yeah.
That fundamental difference between a chemical reaction and a nuclear one.
Yeah.
It's just completely different rules.
Like comparing apples and oranges, or maybe apples and plutonium.
Yeah, something like that. So let's start basic. What is a nuclear reaction, fundamentally?
Well, unlike chemical reactions where atoms just get rearranged, a nuclear reaction involves changes in the nucleus itself, the core of the atom.
So adding things, removing things.
Precisely, adding or removing particles like protons or neutrons, or maybe just releasing energy as radiation. It's about restructuring that core.
And you mentioned these aren't just theoretical concepts.
Oh, not at all. They're absolutely vital. It's how elements heavier than hydrogen and helium get made in stars. It's the energy source for nuclear power plants.
And medical uses too, right?
Definitely. Diagnostics, treatments. Nuclear processes are key. They really shape our universe and how we interact with it.
Okay, let's really pin down that difference. Chemical reaction versus nuclear reaction. First big point, identity change.
Right. In chemical reactions, think burning wood, rusting iron, the atoms swap partners, bonds break and form, but an oxygen atom stays an oxygen atom. Always.
But nuclear.
Nuclear reactions are where the magic, or maybe the alchemy, happens. Atoms of one element can, and often do, literally transform into atoms of another element. That's transmutation.
Transmutation. Okay, that's a huge conceptual leap. What about the particles involved?
Also totally different. Chemical reactions are all about the outer electrons, the ones involved in bonding. The nucleus just sits there, uninvolved.
But in nuclear reactions.
It's the opposite. The action is in the nucleus. Protons, neutrons, other little particles buzzing around in there. The electrons on the outside, they usually don't play a role.
Got it. Then there's energy and mass. Chemical reactions, relatively small energy changes, right? And mass seems constant.
Yeah, the energy changes are modest, and any mass change is far too small to measure. But nuclear reactions, whoa, huge energy releases.
Nice measurable mass changes, really.
Yes, tiny but measurable changes in mass. We'll get to why later, but it's tied to that incredible energy release, EMC thaw, that whole thing.
Okay. And finally, reaction rates. Temperature, concentration, affect chemical rates.
Right, catalysts too. But nuclear reaction rates, they pretty much just depend on how many radioactive nuclei you have. Temperature, pressure, catalysts, they don't really care.
So it's an intrinsic property of the nucleus itself.
Exactly. These differences show we're dealing with something fundamental, operating at a much deeper level of matter. It's why the applications and implications are so profound.
Okay, so if we're changing nuclei, we need a way to write that down precisely. Let's talk symbols. Nuclear symbols.
Yes, because isotopes matter here. It's not just carbon. It might be carbon-12 or carbon-14, so the symbol needs to show that.
Standard format is the element symbol, say X, then mass number top left, atomic number bottom left. Mass number is protons plus neutrons.
And atomic number is just protons.
Right. Now, just for clarity while we're talking, we're going to read these out simply as element and mass number. So instead of the full symbol for uranium-235, we'll just say uranium-235. Makes it easier to follow along.
Good plan for audio. And a couple of terms are useful here. Nuclide just means a specific type of nucleus, like uranium-235 is a nuclide.
Okay.
And nucleon is the general term for anything in the nucleus. So protons and neutrons are both nucleons.
Got it. So what are the common particles we see popping up in these nuclear equations?
Well, there are a few key players. You've got the electron, but when it comes out of the nucleus, we often call it a beta particle. Symbol E or beta. Charge is -1. Mass is essentially 0 for balancing purposes.
Okay.
Then the proton, symbol P, or sometimes H for hydrogen nucleus. Charge +1, mass 1.
The neutron. Crucial one.
Symbol N, 0 charge, mass 1. Then the alpha particle, that's actually a helium nucleus, symbol alpha or He, charge +2, mass 4.
Helium nucleus, okay.
There's also the positron, like an electron but positive, symbol E or beta, charge +1, mass 0.
Anti-electron, basically.
Sort of, yeah. Then gamma rays, pure energy, symbol gamma, 0 charge, 0 mass. And sometimes you see a deuteron, which is just a heavy hydrogen nucleus, 1 proton, 1 neutron, symbol H, charge 1, mass 2.
All right, so those are the building blocks for writing these reactions.
Exactly. Knowing these lets us decode what's happening.
Okay, let's get into the types of reactions. 4 main ones mentioned: radioactive decay, nuclear bombardment, fission, and fusion. Let's start with radioactive decay.
Right. Radioactive decay is basically when an unstable nucleus just spontaneously changes to become more stable. It does this by spitting out radiation particles or energy.
Why are some unstable? Too many protons, too many neutrons.
Exactly that. An imbalance. Too many neutrons for the protons or vice versa, or just too big overall. Decay is this way of adjusting the ratio or size to find a more stable, lower energy state. And this process, remember, where one element turns into another through decay, that's transmutation again.
Okay, and there are different ways it can decay.
Yep, 5 main types listed: alpha emission, beta emission, positron emission, electron capture, where the nucleus actually grabs an inner electron, and gamma emission, which is just releasing energy.
Each one ejects something different.
Correct. And that determines what the remaining nucleus looks like.
So how do we write these out and make sure they're correct? Balancing.
The golden rule. It's actually quite straightforward conceptually. 2 things must balance on both sides of the reaction arrow. The mass numbers must add up, and the atomic numbers must add up.
So total protons and neutrons conserved and total charge conserved.
Precisely. It's like nuclear bookkeeping. Let's take an example from the source, alpha decay. Polonium-212 decays.
Okay.
It becomes lead-208 plus an alpha particle. Remember, an alpha particle is helium-4.
Right, mass 4, charge 2.
Exactly. So check mass numbers. Polonium is 212. On the right, lead is 208. Helium is 4. 208 plus 4 equals 212. Balanced.
Okay.
Now, atomic numbers. Polonium is 84. Lead is 82. Helium is 2. 82 plus 2 plus 2 equals 84. Balanced again. See?
Yeah, that works perfectly. It's consistent.
Let's do beta decay. Cesium-137 decays to barium-137 plus a beta particle. A beta particle is like an electron, mass 0, charge -1.
Okay.
Mass numbers. Cesium is 137, barium is 137, beta is 0.137 plus 0 equals 137. Balanced.
Yep.
Atomic numbers. Cesium is 55, barium is 56, beta is -1. 56 plus -1 equals 55. Balanced again.
It's neat how that negative charge works in the balance.
It is. And the same balancing principle holds for everything positron emission, like oxygen-15 decaying to nitrogen-15 plus a positron.
Where the atomic number goes down by 1.
Right. Or even more complex things like bombardment reactions, where you hit one nucleus with another particle, like making phosphorus-30 from aluminum-27 and an alpha particle. Or fission, like uranium-235 splitting. Mass and charge always balance.
It's the fundamental grammar of nuclear reactions.
You could say that, and it all ties back to this idea of nuclear stability. We often talk about the neutron-to-proton ratio, or NZ ratio.
NZ ratio.
Yeah, there's this sort of sweet spot for stability. For light elements, say atomic number below 20, stable nuclei have roughly a 1-to-1 ratio, 1 neutron for every proton, more or less.
But it changes for heavier ones.
It does. As you get heavier, stable nuclei need progressively more neutrons than protons. The ideal NZ ratio climbs above 1.
Why is that?
Why?
More neutrons.
Good question. It's about balancing forces inside the nucleus. You have the strong nuclear force, incredibly powerful, short range, holding all the nucleons, protons and neutrons, together.
Okay, the glue.
Right. But you also have the electrostatic force, the repulsion between positively charged protons pushing each other apart. That force is weaker, but acts over longer distances.
So as the nucleus gets bigger.
That repulsion between all those protons builds up. Neutrons add to the strong force glue without adding any repulsion because they're neutral. So they kind of dilute the proton repulsion. Heavier nuclei need that extra neutron padding to hold together against the proton push.
That makes intuitive sense. More protons need more neutral spacers to keep them from flying apart.
Essentially, yes. And all these stable nuclides fall within what we call the band of stability. On a chart of neutrons versus protons, anything outside that band is radioactive. It will decay to try and get back into the band.
So if a nuclide is above the band, too many neutrons.
Correct. It'll likely undergo beta decay. A neutron turns into a proton, emitting an electron, beta particle. This decreases neutrons, increases protons, shifting it down towards the band.
And if it's below the band,
Yeah.
too many protons.
Then it needs to get rid of positive charge or gain neutrons. So it might undergo positron emission. A proton becomes a neutron, emitting a positron. Or electron capture, grabs an electron, turning a proton into a neutron. Both increase the NZ ratio, moving it up towards the band.
And really heavy ones, above atomic number 82, like lead.
They're often just too big overall. They tend to undergo alpha decay, shedding a chunk of 2 protons and 2 neutrons, the alpha particle, to get smaller.
Fascinating. So decay is driven by this quest for the stability sweet spot. How fast does this happen? That brings us to decay rate and half-life, right?
Exactly. Radioactive decay follows what we call first-order kinetics, meaning the rate at which a sample decays depends only on the number of radioactive nuclei present at that moment. More nuclei, faster decay. Fewer nuclei, slower decay. It's not influenced by temperature, pressure, etc., like chemical reactions.
Okay. And the decay rate itself is just how many nuclei pop per second, basically.
Yep, that's the activity. And the crucial measure related to this is half-life.
The time it takes for half the sample to decay.
Precisely. And the key thing is, for a given isotope, the half-life is constant. Doesn't matter if you start with a ton or a microgram, the time for half of that amount to decay is always the same. Short half-life means it decays quickly. Long half-life means it sticks around.
What units do we use for decay rate?
The standard unit is the becquerel, BQ, which is simply 1 decay per second, a very small unit. More common historically and still used is the curie, CI. 1 curie is 3.7 times 10 to the 10th becquerels. So 37 billion decays per second. That's a lot of activity.
Wow, okay. So knowing the half-life, what can you do with that? How is this useful?
Oh, hugely useful. The classic example is radioactive dating, specifically radiocarbon dating.
Using carbon-14.
Exactly. See, living things constantly exchange carbon with the environment, so they maintain a steady, known, tiny proportion of radioactive carbon-14. But when an organism dies, it stops taking in carbon. The carbon-14 it already has just starts decaying with its known half-life.
And the half-life of carbon-14 is?
About 730 years. So by measuring how much carbon-14 is left in an ancient sample bone, wood, cloth, compared to how much was there originally,
You can calculate how long ago it died. Like a clock stopping.
it's exactly like a nuclear clock. The source gives a great example. Some charcoal from a tree killed in a volcanic eruption. They measured its carbon-14 activity at 7.0 disintegrations per minute per gram.
Okay.
Living things typically have about 15.3, so it's roughly half gone. Knowing the half-life is 730 years, you do the math.
And it tells you the eruption was?
Around 6,500 years ago.
Yeah.
Pretty amazing precision from decaying atoms.
That really is incredible. Okay, so that's decay. What about the other types? Nuclear bombardment. Sounds aggressive.
It is, kind of. You're deliberately hitting a nucleus with another particle, maybe a neutron, a proton, or even another nucleus to force a reaction.
Why would you do that?
Primarily to create new isotopes, especially artificial ones that don't exist naturally or exist in very small amounts. The very first artificially produced radioactive nucleus, phosphorus-30, was made this way back in the 30s by hitting aluminum-27 with alpha particles.
Aha.
It's also how we make the transuranium elements, all the elements heavier than uranium on the periodic table. They're synthesized by bombarding heavy nuclei.
Right, creating new elements in the lab. Now, fission. That's the one most people associate with nuclear power, right? Splitting the atom.
That's the one. Fission is when a very heavy nucleus, usually something heavier than mass number 200, like uranium-235, absorbs a particle, typically a neutron, and becomes unstable, causing it to split into 2 or more smaller nuclei.
And the key thing is?
Energy. It releases a tremendous amount of energy, but also, crucially, it releases more neutrons, typically 2 or 3.
And those neutrons can then hit other uranium atoms.
Exactly, and cause them to fission, releasing more energy and more neutrons, which cause more fissions. That's the chain reaction.
Self-sustaining.
Potentially, yes. If you have enough fissionable material packed together, what's called the critical mass, the reaction will sustain itself, releasing enormous energy. That's the basis of nuclear reactors and, unfortunately, atomic bombs.
The source example was uranium-235 plus a neutron, making strontium-90, xenon-143, and 3 neutrons. Those 3 neutrons keep it going.
Precisely. Controlled in a reactor, uncontrolled in a weapon.
Okay, so if fission is splitting things apart, fusion must be.
Putting things together. Fusion is combining small nuclei, like hydrogen isotopes, to form larger ones, like helium.
Where does this happen?
The sun and all stars, that's their power source. Inside the sun, the immense pressure and temperature, like 15 million degrees Celsius, force hydrogen nuclei to fuse into helium.
Releasing even more energy than fission.
Per mass, yes, fusion releases even more energy. It's the ultimate energy source, really. We're trying hard to replicate controlled fusion here on Earth for clean energy, but it's incredibly challenging because you need those star-like temperatures and pressures.
Right. A mini sun in a box.
Yeah.
Tough engineering challenge. So this brings us back to the energy. These reactions release so much more energy than chemical ones. Why?
It comes down to Einstein. Energy equals mass times the speed of light squared.
A famous one.
Right. What it means in this context is that mass and energy are interchangeable. In nuclear reactions, a tiny amount of mass is actually converted directly into energy.
So the products weigh slightly less than the reactants.
Exactly. That tiny difference in mass is called the mass defect. It's the mass that got converted into the energy released, according to EMC Alish. And because c squared, speed of light squared, is a gigantic number, even a minuscule mass defect translates into a huge amount of energy.
Wow. And this relates to stability.
Yes. That energy released when a nucleus forms from its protons and neutrons is called the binding energy. It's literally the energy equivalent of the mass defect. It's the energy that holds the nucleus together.
So more binding energy means?
More stable nucleus, because more mass was converted into energy when it formed, meaning it's in a lower, more stable energy state. We often look at binding energy per nucleon to compare stability across different elements. Iron has one of the highest binding energies per nucleon, making it very stable.
So fusion of light elements releases energy moving towards iron, and fission of heavy elements also releases energy moving towards iron from the other side.
You got it. Iron's kind of the stability peak in the middle.
Mind-bending stuff. Okay, let's try and pull this all together. We've covered a lot in this deep dive into nuclear chemistry.
We really have.
We started with what it even is, reactions inside the nucleus, and how drastically different it is from regular chemistry. That whole idea of transmutation, elements changing.
Yeah, fundamental difference. Then we got into the language. The nuclear symbols needed for specific isotopes, the key particles like alpha, beta, neutrons.
And the all-important balancing act. Mass numbers balance, atomic numbers balance. That rule underpins everything.
It does, and that connects to stability, the NZ ratio, the band of stability, and how different types of decay, alpha, beta, positron, are just ways for unstable nuclei to get back into that band.
We talked about measuring decay rates, activity, and that crucial concept of half-life.
Which leads directly to amazing applications like radiocarbon dating, using decay as a clock.
Then we looked beyond decay at bombardment. Fission splitting atoms, chain reactions, critical mass and fusion, sticking them together like in the sun.
And finally, tying it all together with the immense energy involved, explained by immensity, mass defect, and binding energy holding the nucleus together.
It really shows how these, almost infinitesimally small changes deep inside an atom can have just enormous consequences.
It's staggering, isn't it? The energy powering stars, the ability to date things thousands of years old, the power generation, the medical tools, even creating brand new elements, all driven by rearranging protons and neutrons.
It really is. So maybe a final thought for everyone listening. When you think about this incredible power locked inside the nucleus and our increasing ability to manipulate it through fission, fusion, bombardment, what does that mean? What new possibilities does it open up for energy, for science, for understanding the universe? But also, what responsibilities come with that kind of power? It definitely makes you think about the hidden potential packed into the tiniest bits of matter all around us.